it's 10:03. Let's get started. Can everyone hear me okay?
Yep.
Great. Well, welcome to the August edition of the South Atlantic LCC's Third Thursday Web Forum. I'm Hillary Morris. If you guys frequent this call, you probably hear from me once a month. I work on Blueprint user support and communications for your cooperative. Most of you are probably familiar with the logistics for these calls, but this is a monthly event. Your cooperative hosts a web forum on the third Thursday of each month, featuring either updates from staff or a presentation on other exciting and relevant work going on in the South Atlantic region. We hold it every third Thursday at 10 a.m., and it's a great opportunity to get involved in your cooperative. So first, I'll introduce our presenter, and then after they talk for 30 or 40 minutes, we set aside a block of time for any questions, and the remaining time will include updates from your cooperative, followed by an open discussion on what the South Atlantic LCC has been up to. So as usual, I'm going to mute everyone during the presentation, so if you have questions, just type them directly into the chat box and I'll monitor that, or you can hold them until after the presentation. And just keep in mind that to speak at any time during the discussion, and Ashton, as presenter, this includes you, you'll just have to press *6 to unmute yourself. So are there any questions before I mute everyone? Okay, hearing none.
The conference is now in silent mode.
So presenting today, we have Ashton Drew, who is the owner and lead consultant with KDV Decision Analysis. And you may recognize her from her former life with the Biodiversity and Spatial Information Center at NC State University. We're particularly excited to have Ashton today because she got up at the crack of dawn in the Yukon province of Canada today to be with us, and has even braved a lack of electricity to be here this morning. So she gets extra thanks for being here. Ashton, are you ready to get started? Just *6 to unmute. Ashton, if you're talking, I don't think we can hear you. Just press *6 to unmute your phone.
Hello?
Hey, there
Hello?
you are.
Okay. Yep, no, sorry, I did #6, not *6. Yeah, so good morning, everyone. It's rather early here, but I'm excited to have the chance to talk to you. And because I am off the grid, I have power at home. I just don't have internet connection to the outside world. So Hillary's going to be, I'll be telling her next slide, and I won't be able to see the chat thing, but she's going to monitor that for me, and hopefully things will go smoothly. It's kind of just part of life in the bush. So anyway, today I'll be presenting some work that we did for the SALCC. It was on freshwater aquatic conservation problems and challenges, especially for endemic species. And as I'll show you, we focused especially on mussels. And I'm just going to highlight some of that research. Our report hopefully will come out on maybe Monday. It's passed through all of its review stages, and I just have 1 or 2 more edits to make to the PDF. And I'll provide contact information at the end if you'd like to send me an email to make sure you get that once it's free to be dispersed. And this work was done with co-PIs Tom Kwok, Greg Cope, and Tom Augsburger. And I also just want to mention special thanks to folks who provided some data sets that you'll see. These were Tamara Pandolfo, Rob Nichols, Michelle Itty, and Curtis Bellier and Ernie Hain. But otherwise, I will just get started. And so next slide, I'll remember to say that. The starting point for this was that the SALCC faces a lot of decisions related to freshwater aquatic species conservation throughout their region. There are many threats, and these threats require management if we're going to conserve the species. And the species in this area are extremely diverse, and many of them are rare endemics that are also endangered. And so we know often where these species are. There's been huge efforts to do surveys, especially of wadable streams. But even when we know where they are, and there might only be a few populations, we don't always know if the places they remain are actually suitable, or if there may be legacy effects or failure to reproduce. So it can be difficult with very few points and then uncertain points in terms of quality to use traditional correlative sort of approaches to modeling habitat. And we also know that what's suitable today, given landscape and climate changes, which are rapid in the southeast, we may want to have an approach that allows us to more effectively and remotely monitor changes in landscape or assess the effects of changes in landscape. And so part of this project is developing that landscape approach. So it's kind of a pilot project. We worked in a smaller area, not the entire SALCC, as you'll see. But I'm hoping that rather than focus on some of the very details of the modeling effort, we can focus on the approach itself if folks have questions. But I'm happy to take questions on both. But what basically we're trying to do is we have these decisions and they need to know where to do them, what to do and where to do it. So next slide, please. And these questions can sort of be summarized into sort of three categories. The first is how to allocate effort. The efforts that we might make more surveys. We might protect populations that we know are already there. We might try to restore populations in areas that were in the historical range, either through augmentation or if they're still there, but we know that the habitat is not so great, trying to improve it. For some species, we can now do captive breeding. Maybe we would try to release species or take species from one area that we think we can't restore, but where they're present, and relocate them to someplace better. Obviously, some of those have some ethical, broader considerations to think about. And then also doing nothing, which is actually a choice that you're making by default when you're not doing the other actions. So where to allocate this effort, though, requires fine-scale knowledge at broad extent, and also a sort of mechanistic knowledge. If you're just wondering whether to protect, to acquire habitat, you may not need that mechanistic knowledge, but when you start trying to determine if you can do restoration, you need to have a little bit more of a mechanistic view because you're thinking that conditions are unsuitable, but are they unsuitable in a way that you can actually improve? And you're making then predictions about the likely improvement and in both the amount of improvement and the direction of improvement, I guess, that you could have. So that requires a little bit more mechanistic, of a mechanistic hypotheses to be involved. And finally, if we're going to do sort of strategic habitat conservation, cycle of conservation and adaptive management approaches, we need to have some way for how to judge success of our effort. And this requires clear testable criteria, both for predicting condition of the habitat and for predicting the suitability of that condition. And I'll talk a little bit more about why I separate those out later. So next slide. So the starting point, as I said, for us was also with mussels. We chose to work with mussels because they they present a lot of information and they've been the focus of significant research effort. Since 1997, when there was a national strategy for the conservation of freshwater mussels, a lot of work has been done on them, especially in North Carolina. And in 2014, Haig and Williams gave a review of this progress, and they summarized some of the great gains in knowledge of basic biology, knowledge of distribution, even identifying new populations for some of these rare and endemic species, a lot of work in toxicology, and also, and this one will be important, in propagation, so that for many species of mussels, we now have developed systems where we can either grow them out in lab facilities or also breed them and grow them out in lab facilities. So next slide, please. And there's two areas, though, that he felt required increased attention. And the first of these is sort of increased attention to causes of decline. So why have they disappeared from places in their historical range? And also closely associated to this, opportunities for restoration and translocation. So again, more attention to this landscape scale, broader process picture. And then also, as part of this, increased attention to document management efforts and outcomes. So this paper wasn't out when we started. We started in 2011 on this work, but many of the people involved obviously were also involved in developing our project, and the awareness of the literature was the same in both cases. And I feel that both of these sort of two concerns, the need for a landscape approach and the need for a sort of framework to improve our knowledge of management effects and efforts and outcomes, were sort of guiding principles that we had in developing our approach. So next slide, please. So the study area that we worked in and the species that we primarily focused on, we worked in the Tar and Neuse River basins, which are shown here. The Tar is the northernmost river, and the Neuse is the one underneath. The Neuse has Raleigh towards its upper reaches. And we only worked in the non-tidal portions. for this muscle. It doesn't occur in the tidal portions, and also the hydrological data that I'll show you only is available for the non-tidal regions. And the Tara River spiny mussel was our focus species. We also considered some of its associates, the yellow lamp mussel, and I'm going to go blank on the second one, but I'll have its name later. But primarily we focused on the Tara River spiny mussel. And this is because it's a great example of a rare endemic species. It's one that we can now grow out in the aquaculture facilities. So we actually have, I would think of them as I worked on this project when I was feeling stressed out, as $1 million buckets of mussels that we're going to put out someplace, and they're going to live or die based on my models when I was giving myself a hard time, but hopefully more likely to live than die. So next slide, please. So the general approach, this is a very big picture overview, but we started with a design workshop, which was a gathering of regional mussel experts and also stream habitat experts. And when I do these sorts of projects, I am not an expert. I don't come in as a mussel expert or a freshwater ecology expert. So these design workshops are my immersion into the knowledge that's available. The goal of my models is to assemble all this knowledge and data. So it's learning the language and also learning the scales at which people think, the relationships between the knowledge units that they've gathered, and also doing a huge characterization of experts' knowledge itself. I won't talk so much about that part of it, but it is included in the report. But based on input from this design workshop, they've given me thousands of sources to go search for data and experts to talk to. I try to assemble all of that information, the existing mussel and water quality and landscape level spatial data, and expert knowledge more formally. So the design workshop is not so much a formal elicitation, but part of this project later includes formal individual expert elicitations as well. And then finally, the goal is to develop models and maps that can inform the decisions within an adaptive management context. So to go from these crazy whiteboards of connected lines everywhere to something that looks pretty like a map. So next slide, please. And so there's 3 models that I'm going to run through. I'll spend the most time on the first and the last, since the second kind of follows the same methods as the first. But I'm, again, just going to sort of highlight what these models look like and not go into a lot of the details. The first 2 will be Bayesian network models, and these are for temperature, the probability of suitable temperature and water quality. Bayesian network models are great models for adaptive management settings. They're probabilistic models. They can accommodate both empirical data and expert knowledge easily. And they're designed to be updated. As you input new cases, the models can update their predictions. However, they also are, the more variables that you put in, the more complicated they become, the more difficult they are to parameterize. And so we also have an ordination model, and with this we use the hydrology data from waterfall models from the Research Triangle Institute. And this was partly because there were so many possible ways to slice and dice hydrology data and so many variables that the model would have been very unwieldy to use expert knowledge in that case. So next slide, please. And I need my next slide. Okay. So straight into the first model, which will be for suitable temperature. I mentioned just really briefly that I separate out predicting condition from predicting suitable conditions. And this will give you an idea of what I mean by that. So for each of the Bayesian models, both of the Bayesian models, there is a very specific target definition. This was something that, this is one of those cases where I think you may or may not agree with this if you're on the phone as an expert in mussels, especially Tara River spiny mussel. So for example, we said that the daily minimum temperature measured at 10 centimeters below the substrate surface does not exceed 28 degrees Celsius for more than 96 hours. This, like I said, very specific. And there's some more details in the report about how this might be measured or when it might be measured in terms of season. But for a model to be validated, or for adaptive management, a model has to be able to be validated. And to be validated, when I make my prediction, I have to say, how would this prediction be measured in real life? So when my experts are elicited for their prediction of what's the probability of suitable temperature under a suite of conditions, they're not just thinking of, they could each have a different definition of what suitable temperatures might look like, in which case my model is predicting a broad range of possibly very different things measured in very different ways. So instead, I'm very specific in asking the experts not what's the probability of suitable temperature, but what's the probability of meeting this particular sort of exceedance threshold. And separately, there can be work done to determine if this really is a good exceedance threshold for this individual species. So next slide, please. You can sort of see, so when a model is made to predict suitable conditions or to predict for occupancy, predict for these things, there's often two sort of hypotheses inside that broader prediction. And I'm wanting to be able to get at those separately in the adaptive management process when you guys go out and start, putting mussels out there or going to visit sites that we thought might be suitable or unsuitable. The first question is, can we remotely predict the probability of exceeding a particular threshold using spatial data, these large spatial data sets? Or is the only way to predict this to maybe be in the field and to set up long-term monitoring stations? But this first part of the question is primarily answered through going out and doing field work to validate the models, and also through monitoring management over time. The second half of the question, though, is whether it really is the exceedance threshold for a particular species. And that's primarily answered through lab work, although field work can also be important, especially with the opportunity to put mussels out in cages and look at their stress or survival. And so this was why we have these very specific definitions, which possibly not everyone agrees with at this point in time, but it allows us to test the ability to use remote data in a useful way to predict condition. Also, one of the goals of this project was not, even though we're working with Tar River spiny mussel and other mussel species, we wanted it to be much more general for benefits to aquatic species. And the first question, can we predict condition with remotely sensed data? As we get that more precise and accurate, that ability to predict more precise and accurate, that benefits all species at the same time. The second question of exceedance thresholds always is species specific and needs to be addressed species by species by species. So hopefully that makes sense, and I can take questions on that because it is a really important point in how we set up the models. So next slide, please. So this is a sort of cartoon of what the suitable temperatures model looks like. Basically, we have a lot of spatial data sets that experts thought might be relevant to making inferences about whether temperatures would or would not exceed certain thresholds. Some of these were considered to be the intermediate nodes are what experts actually predicted for. And these were the sort of where we tried to incorporate mechanisms. So we have some data that we thought would allow us to make inferences about buffering mechanisms, maybe shade, stream order, groundwater input, for example. And then there were three sort of threat mechanisms: water extraction, sustained thermal inputs, and pulsed thermal inputs. So connected, and this is where I wish I could use a pointer to show you, but going into the extract node, you can see that there's water use permits, there's row crop land cover, and urban land cover. Going into the sustained thermal threats, there's thermal effluent permits, and also urban land cover. And then into the pulsed threats, there's urban land cover and road crossings per river kilometer. And one of the things you'll notice that there's certain variables also in this model that occur multiple times. And where they occur multiple times, this is also critically important because if you think of, for example, urban land cover, you can potentially have urban land cover is going to change and affect temperature potentially in different ways and at different scales. So the immediate, on a hot summer day, the absence of riparian shade, the amount of impervious surface potentially is increasing the temperature, but changes in flow rates are also potentially increasing the temperature. And if those are occurring at different scales and at different times, they potentially, one of our questions is the potential for restoration, we would need to know which of those were occurring and whether it could be influenced or not. Perhaps the amount of impervious surface can be affected with how people manage residential or urban landscapes, but the presence of just urban cover in general can't really be reduced. And I think I'll go to, well, all of these together. So the experts, what they did was they would receive a set of scenario-based questions. So for the buffering, they would get for a certain percentage of riparian forest cover and a certain size stream order and a certain percentage of input from groundwater, what's the probability that buffering, that a lack of buffering, rather, would cause us to exceed the temperature threshold? Then they would receive another scenario with a different percent cover or a different stream order or a different groundwater input. They'd go through a lot of questions. This is very intensive on the experts, and give the probability of exceedance just considering the buffering conditions. And they would give me the sort of, if I surveyed 100 sites with these conditions, how many do I think, my best guess of how many would exceed temperature threshold, what's the absolute minimum that would exceed the temperature threshold, the absolute maximum number of sites that would exceed the temperature threshold. And using those, we can make a beta distribution and then also estimate betas for mixed model regressions, which are the backbone of the model. And again, I don't want to go too much into that, but I'm happy to take questions at the end. But then I combine those four, in this case, 4 intermediate nodes to predict the probability of suitable temperature at any given HUC or 500 meter stream reach in the system. So one of the things I said that we did do was to, since this is an expert-based model, was interview our experts on their expertise. There's a bunch of figures related to this. This is just one example of how experts really differ, and they present different strengths and weaknesses in their knowledge relevant to the questions that I'm asking them. This figure shows just the composition of their knowledge in terms of source. So whether it came from direct field observation and research, whether it came through observation that might be monitoring but was not an experimentally designed testing relationships kinds of observations, and then whether it came from literature review and discussion with colleagues. And it's important to note that one of the reasons I ask this, I guess, is that when people have done their own empirical research and direct observation in their programs, we often can see differences, and those differences might be important, represent important ecological differences between where they've sampled and when they've sampled. Whereas they're less, if it's primarily literature review and discussion with colleagues, they're less likely to show strong differences in their opinion, because often I'm pseudo-sampling. I'm getting the same information twice from 2 experts, potentially. So we also ask them about, so we have these different nodes and topics. We ask them how often were these variables that they considered in their work in relation to water temperature. And so you can see that sometimes, like groundwater, this is for expert 1, was something that they never really thought about or considered in the work that they do, but their focus was primarily on land cover and effluent and riparian shading. Not surprising, because a lot of the water temperature knowledge comes through folks who work more with permitting and trying to know what temperatures are considered safe or not safe for aquatic systems. So next slide, please. So the ultimate prediction of these models will be our maps, but this is just a graphical representation of data in the map, and I wanted to show it. This is, again, one where I wish I had my pointer, but what you're seeing is that these are the probability of suitable temperature first for each of the individual threats or buffer nodes. So the red lines are the probability of suitable temperature if we only consider that individual threat. The blue line is for if we only consider the buffering and the data that we thought allowed us to make inference about buffering. Then the black line is the data that you will see on the map. It's the probability of suitable temperature given all information. And with the red lines being mostly to the right of the graph, shows that experts didn't really feel that, in this landscape anyway, that there was a huge threat from these individual threats when we looked at a Huck scale. But they did feel, because the buffering is going more to the left, that there was quite a bit of threat potentially from loss of or from low values in the buffering data. And then when we put it all together, it's a little bit in the middle. And underneath what you're seeing is, and I'll show these again in a different graph, but this is a quick look at the validation data sets that we had. So for this temperature models, we had 2 validation data sets. There was the temperature surveys that were part of mussel surveys conducted by Tamara Pandolfo for her PhD research. And so she used my definition of exceedance and the method that we described. So she was able to say whether they were suitable or unsuitable given that definition. And here we see what we'd like to see. We hope that sites that exceed the temperature end up going to the left of the graph. The red dots are the triangles. The unsuitable sites are generally to the left of the suitable sites. Because this is expert knowledge, we found that experts don't necessarily, at this point, have the knowledge to predict the exact temperature, but they do seem to be, and they can be very different in which sites, in the absolute score that they give to sites, but the relative ranking among experts, despite their different knowledge and despite their different absolute scores, the relative ranking of sites was very similar. So then we also had the Wildlife Resource Commission mussel survey data. So we have sites where the Taraver spiny mussel were detected and sites where they were not detected. And here we see a little less of a pattern for the temperature predictions. Ideally, we'd have the same sort of shift where detections would occur mostly to the right of the graph, and non-detections can occur throughout, which is okay. Mussels might not be present for a number of reasons besides temperature, but we would hope that they only occur at sites that have the highest probability of suitable temperature. They are all occurring above 0.5 probability of suitable temperature, which is good. But when we look at these data, it sort of suggests that maybe we could improve our definition of, we're good at predicting landscape condition, but we're less good at predicting for mussels. So possibly our definition of suitable conditions is a little off. And so here, this is what the map products end up looking like. And basically, you've got red means that sites have low predicted temperature suitability. Yellow has high predicted temperature suitability. And then on the right is the standard deviation, so your confidence. And I always think of the grayscale as being like the more muddy the waters, the less confident and clear we are in our predictions. So that's the higher standard deviations. And the way this would sort of be used is that you can look at, if you were looking just at temperature for now, you can look for good sites. And if you have good sites that have mussels, these are candidates for protection decisions. If you have good sites without mussels, these might be candidates for restoration or reintroduction, so worth going to visit. And because you have the mechanistic model, you can see if they're good sites, but the mussels aren't there, we'll have this product plus the other map products that we made for the other variables to see if something is there that we can fix. But if it's a bad site, a low scoring site, and it has mussels, maybe these would be candidates for relocation or restoration. And again, mechanism becomes important here because restoration is only possible if it's scoring low for a variable that is something that can be reversed. It's easy potentially to reforest a riparian zone, but not so easy to remove an urban area. So that's one more figure, so next, sorry, and I keep forgetting to say next, since I can forward them. So hopefully you're looking at a slide that has temperature validation figures, 2 of them.
Yep, we're
and this
good,
just,
yeah.
Pardon?
Yeah, we're caught up with you. We're all good.
Okay, sorry. All right, I had a page that I had written next on top of, and then I flipped that off my notes. So for temperature validation, this just shows the same data that was hard to read underneath the other figure, showing where suitable conditions generally, the sites that we gave the highest prediction for turned out to be suitable, and lower predicted sites were unsuitable, so that's good. We're good at predicting condition, but that the mussels themselves, we did not see mussel sites pulling out ahead of the non-detection sites. And again, that suggests that possibly our threshold criteria is off. So very quickly, I just want to run through the suitable water quality. I'm not going to go into detail on this so much explaining the figures, but just to get to the maps. So again, very specific definition we have to know if there's suitable water criteria. We can't, in this case, specify a number like we did in temperature, because water quality is so many things. So instead we go with an IBI index, so saying that the biological index is excellent, using the North Carolina Index of Biotic Integrity for fish. And we use the fish because we need to know about fish hosts anyway. So this is thinking about effort available for doing adaptive management, as well as the information that we need for these models. But also, it's both of these things that, because we're not sure of the relationship between IBI and the mussel itself, we need to also confirm presence of a reproductively successful population of the associated species, so either the yellow lance or the one that I was blanking on before, the Atlantic pigtoe, or because we have these mussels that we can potentially put in cages to test, survival and growth of captive bred juvenile tarver spiny mussel introduced and monitored for at least 1 year. So this would be our method to validate the model. Next slide. Again, the structure of the Bayesian network model is that we have spatial data, which feed into, in this case, threat nodes. Our threats were pesticide threats, ammonia threats, eutrophication threats, pharmaceutical threats, hydrocarbon, and metal threats. And experts answered scenario questions to score each of these intermediate nodes, and then I combine those to predict the overall probability of suitable water temperature. The data that we had were a lot of permitting data and, again, land cover data. So next slide, please. And again, we get a figure that shows we can look at, there's this graph as well as maps for each of the individual threats. So here, things like the blue is far on the right. So the hydrocarbon threats and the heavy metal threats, they didn't feel that these were relatively minor, having a minor effect. But if you look at the yellow and the red, these were stronger. So pesticides, pharmaceuticals, ammonia, and eutrophication were given stronger scores by the experts. And the all information combined is the black line. And again, the validation sets shown on the bottom, but there's a different pattern here. Here, we don't see the separation in condition, our IBI index. High excellent scoring versus scoring anything except excellent don't really separate out. We found out later this is because good and excellent actually, you have an equal probability of being predicted to be good and excellent in our landscape, and if we merge together the good and excellent scores, then we do get good division. But we do see a good ability to predict for our detections of tarver spiny mussel. They occur clumped in the high end of the probability of suitable water quality. So next slide, please. This is just the same sort of figure. We have the predicted value for probability of meeting the IBI criteria and the standard deviation on those predictions. And these ones in water quality, you see the fall line coming through the middle of the state, where the southeastern portion is predominantly agriculture and the northwestern portion of the state has a lot more forest and urban areas. So different conditions for water quality, which was interesting. Next slide, please. So that was very quickly through water quality, just because I wanted to be able to also touch on the hydrology. As I mentioned, this is a very different model. It's not a Bayesian network model. Hydrology was simply too complex of an issue to ask experts. We would have had a network that was interconnected all over the place. So instead, we have this great new data set, waterfall data from Research Triangle International. And this is a data set that I believe the SALCC is working with, developing at broader scales for the region. So it was also a nice sort of chance to play with it and test out potential applications. What it provides is it models daily mean flow metrics. It can do it from back to 1960 through, I think, 2010. And it does these according to the index of hydrologic alteration. And what we were provided with was threshold, annual mean, and annual standard deviation flow metrics for base flow, rise rate, zero flow days, flow frequency, flow duration, and flow discharge. So if you think for each of those 1, 2, 3, 4, 5, 6 variables, we had the threshold, the mean, and the standard deviation. And there's a lot of correlation between all of these variables. And talking to experts, it often isn't, because there's such strong correlation, it's very difficult to come up with mechanistic hypotheses in terms of which of these variables is driving patterns in mussels. So our goal was to simply do a data exploration at this point to build ordination models, and we used principal component analysis and discriminant analysis. And when I started this out, I was trying to just do discriminant analysis, and the results were very unstable. Every time I ran it, I would get different patterns, different variables being kept in or out of the model. So next slide, please. This, I think, was really interesting and exciting to me as an ecologist working on this. But when I was trying to do the discriminant analysis to begin, I was trying to discriminate between two groups, the detected mussel detections and mussel non-detections for the tar river spiny mussel. And I took it to an expert in ordination. We looked at my data, and he's like, well, have you done a principal components analysis without identifying your groups to see how they cluster? And I was like, well, no. We did that, and what we saw was that there's actually two very hydrologically distinct populations of tar river spiny mussel. This main group is primarily live in third to fifth order streams and have flow characteristics more common to third and fifth order streams. The outlier group, as I call it, group 2, is primarily first order streams. So I know that the Wildlife Resource Commission has done a lot of work with GIS data and trying to find patterns for how tar river spiny mussels relate to landscape characteristics. But they, like me, have been looking at detection versus non-detection, and I think this points to the potential to, and they've tried, above and below the fall line, so Piedmont versus coastal plain, and they've also looked at sort of tar and noose divisions, but this is a completely new division to consider. And it's also interesting from an ecological consideration. There's no second order streams. Are these suggesting that there's two adaptations to two distinct hydrologic conditions, or perhaps tar river spiny mussels used to be throughout, also existing in the conditions that would fall in between these two extremes on this scale, but perhaps those are streams that also have characteristics that make them more likely to be developed for agriculture in urban areas, and so that's where they've been extirpated most heavily from. Anyway, it was interesting, and it suddenly made the other pieces fall into place. So if you go to the next slide, when I reran the discriminant analysis with these two groups, or rather three, so now I have non-detection, the main group of tar river spiny mussels, and my outlier group of tar river spiny mussels, I had a discriminant analysis that gave good results in the rock plot, and also for the training results.
Hey, Ashton, we have a quick
Yep.
question from the chat. Could you say again what type of streams your group 2 was in?
Sure. Group 2 is the outlier group, so that's primarily first order streams. And I wrote that down just to confirm that I have it the right direction. Yes, The outlier group is first order streams, and the main group is third to fifth order streams.
Wonderful, thank you.
Yep. And those first order streams, some of them are in the tar and some of them are in the Neuse Basin, so they weren't geographically distinct, and some of them are in the above the fall line and some are below the fall line, I believe. So the other distinctions, while they were important for water quality and water temperature issues, weren't as important for the hydrology in this particular division anyway. So next slide, please. And just a quick look at so this information has to be used differently in terms of supporting decisions than the Bayesian models as well. We don't really feed data back into an ordination model. And the way I envisioned using this is a very busy slide that I've chosen one section to blow out, hoping that you can see it on your screens a little better. But basically, the plus signs here are places where the Wildlife Resource Commission has not yet surveyed, and therefore we haven't observed anything. So there's lots of sites that have not been surveyed. The open blue circles are also sites that have not been surveyed, but these are sites that are similar hydrologically to sites where we have seen, they have surveyed and have detected the mussel. So the 4 blue dots are the sites that have been surveyed and the mussel has been detected. Of course, they're also similar to sites where they've been surveyed and not detected. Those would be the light blue diamonds. And then I have the same, this is showing group 1, the outlier group, and then for group 2, the main group, I have a similar graph. But this points out these hollow blue circles are sites that are hydrologically similar and have never been surveyed with the mussel survey, so potentially are worth visiting, or at least comparing them to our temperature models and our water quality models to say, well, do we also expect to see a high probability of suitability on those 2 models? Then again, this supports, we only have so much effort we can put out there. Maybe we should start with those sites. It also can help with more research side of things, saying that if we want to look at validating our model with benefits to tar river spiny mussels, maybe we want to focus on these sites that we know are hydrologically similar, and within those find sites that our model predicted to be low, moderate, or high probability of suitability to train our model around predicting for the conditions in the streams. All right, so next slide. We also not only have the graphic data, but the map version of it. So this simply shows where those blue hollow circles were. They're now blue hucks. And what would have been green hollow circles for unvisited hucks for the group 2 are now green hucks on the map. So again, it lays out where you might put your effort in space. So one last quick picture of data, and this is just one of the other questions we had with this project, was looking at species associates. And so in the hydrologic space, we looked at whether the 2 associated species, the Atlantic pigtoe and yellow lance, share hydrologic space. And I think this was also a useful and interesting thing to do, and could be useful where you think you might have other aquatic species associates. Because what we found was that there were a lot of sites that only have the associated species. They're more common. That's not surprising. But where we have group 2 sites, so the 3rd and 4th order streams, or 3rd to 5th order streams, we only ever find tar river spiny mussel with associates. We never find them without. But in group 1, the 1st order streams were equally likely to find tar river spiny mussels with and without its associates. So the value of using associates is potentially greater in the group 2 streams than the group 1 streams. And again, this is a hypothesis that could be tested, and you have it on a map to know where you'd want to go to test it. But it's always important to use associates with caution, and this can help you do that. So next slide, please. And just a few quick highlights to wrap up. What I've shown is that we have some spatially explicit probabilistic, so incorporating uncertainty predictions of suitability and similarity that we think can help inform decisions of where and how to act. And next slide, please. The Bayesian network models specifically support learning from two perspectives. The remotely predicting conditions, the ability to improve our ability to remotely predict conditions benefits all species, all aquatic species. But we also have that improving the precision and accuracy of threshold benefits the individual species one at a time. That requires a little more effort, probably in lab work. And we've wrapped this all up in what we hope is a framework to build upon the success of the 1997 strategy, but specifically to address the priorities outlined in the 2014 review. Next slide, please. And the hydrology model, it complements the Bayesian network models by helping to know where to apply effort, but it also offers novel insights into habitat associations and species associations that we didn't previously have. And a quick, next slide, please. A quick review of some of the other unique features that I tried to touch on, but that it's important we included both non-muscle experts and non-muscle experts, trying to bridge sort of a scale gap or a knowledge gap where muscle experts, we felt they were great. We could put them in a boat and they would stop at suitable sites. They could recognize them and they could describe them, but only at a site scale. They didn't necessarily have knowledge of the remotely sensed data and how that, whether this mussel, what the remotely sensed conditions would be in sites where they saw mussels versus did not see mussels. Or some of our stream habitat experts who didn't know anything about mussels could listen to mussel experts and help us build that picture and make that link more clearly. We characterized the available knowledge and data in relation to the whole study area. That's a chapter I did not touch on, but we have, I think, a very long chapter 2 that summarizes and does data mining of all the spatial data that we used, and even spatial data that we did the data mining to but then didn't use, we included in the report. And we also looked at how that related to sampling effort by the Wildlife Resource Commission. So for each of these variables, we can say whether the Wildlife Resource Commission's knowledge of mussels and their habitat is related to fully sampling the available habitat conditions. We required quantitative estimates, those definitions for habitat suitability, but we allowed for uncertainty. We assumed this model, this is very important, will serve as a starting point for adaptive management model. These models do not necessarily represent truth and should not just be used from here on out forever as if they are true. They're meant to be updated and improved and to be the basis for learning more about mussels and their management, but allowing you to act in the meantime with the knowledge you have. We made separate predictions of conditions, suitability, and occupancy so that we can learn about these separately because they're separate processes. And we incorporated, as much as we could, mechanistic and complicated explanations. And so next slide, please, that's the end. 45 minutes by talking fast. But this is our report, which hopefully will come out on Monday. My email address, should you want to email me directly to make sure that you get a copy when I get the go-ahead to release it. And I'll also release it on LinkedIn and ResearchGate as well. So if you're connected with me there, you'll see a notice come up. And I'm sure the SALCC will put it someplace on their website as well.
Yeah, absolutely.
And I can take questions.
Wonderful. Thank you, Ashton. Yeah, we've got probably 4 or 5 minutes for questions. If anyone wants to ask, just *6 to unmute, or you can type questions directly into the chat box.
Hey, Ashton, this is Jennifer Archambault. I have a question.
Yep.
Okay, you can hear. I wondered if, through the scope of your project, did you have time to then explore the hypotheses related, for instance, to Tara versus Spiny, the first-order stream population versus the third to fifth, or is that like a next step that other folks could take using landscape or contaminant variables and that sort of thing?
If you're talking, Ashton, I don't think we can hear you. You might have muted yourself back.
All right, I didn't know if I had to do it each time or not. So Jennifer, no, we didn't have time to explore those hypotheses further. Obviously, that's kind of the goal, is to look at those in relation to the two other models that we built. A lot of the time in this project ended up going into getting all the GIS data in order, probably 2/3 to 3/4 of the time, and we got as far as we could. But yes, definitely, I hope that this will feed into further research. And even if people aren't doing research directly related to these models, it would be great if such data went back to see if it confirmed the results.
Yeah, that was a really interesting finding.
We actually have a related question from Brett through the chat.
Okay.
Are you aware of anything about the life history of the Tar River spiny mussel or their host fish that would explain the use of the two groups of sites that you found?
No, I don't, but I have data that could be used for that. I have all of I have the IBI results, so I have the fish information, and I've only shown the stuff for Tar River spiny mussels, but I have the 0 and 1 detections for all the other mussels and associates. So in theory, all someone has to do is to take those two groups and take the information from fish surveys and see, to plot red colored dots on top of my other colors and see if there's a relationship in the patterns. And I think it would be interesting to do.
All right, great. Anybody else want to jump in with a question? Probably time for one more. All right, well, thanks for the great discussion, and thanks again, Ashton, for such a wonderful presentation. I'm going to run through a couple of updates from your cooperative before we get off the phone today. First is that we're tackling some indicator revisions this year in preparation for the small update to the blueprint that we're calling Blueprint 2.1. The release of that is tentatively scheduled for June of next year. Rua, do you want to talk about this real quick?
Sure. So the idea is we're going to be focusing, as you probably remember last year, we kind of went through and revised all the different indicators, tested them, and now we're zeroing in on a few of the particular ecosystems that, based on the workshops and feedback from all of you, needed the most work. So we're working on queuing up, doing some data and pre-work behind the scenes on some ecosystems. So you see some of the ecosystems. We've already started a little work on some landscapes indicators in the marine. We're also going to be working on some of the freshwater, aquatic, and waterscapes and plant in the marine as well. So we're doing some work, trying to do a little pre-work this time now that we can focus a little more deeply on some of the indicators and improve some of those depictions. And so there's a sign-up link right there. So for those of you that were part of the ecosystems teams before, so if you're part of the freshwater aquatic revisions or waterscapes or you signed up, we've already got your information, and so we'll be in touch when we're at a point where we're ready to get folks to call and review some different options. If you haven't, there's the sign up link right there, and you can also sign up on the website as well. So we'll be looking at a few different options, and hopefully we'll be able to get to, Ashton was just talking about some of the flows. We now have flow predictions across the entire South Atlantic LCC geography. We almost got to them. They just need a little bit more work in the last revision, and so I'm hoping this year we'll be able to get to a good flow metric indicator as well. So sign up on that one.
Great, thanks. And the next update we have some good news related to the initial funded projects list that's been released for public comment by the Restore Council.
Mm-hmm. Yep. So this is pretty exciting news. So the Restore Council, at least the initial funded project list that I guess went out for public comment, included a project called Strategic Assessment of Gulf Coast Landscapes, and essentially the proposal basically relied very heavily on using the South Atlantic Conservation Blueprint and work going on in the Gulf LCCs to help create a decision tool to guide land protection and restoration in response to the Gulf of Mexico oil spill. So this is a pretty big project that's going to work on integrating those different tools and other information across the geography to create that decision support tool. So not starting from scratch, but building on what we already have. So this is a pretty nice role for the blueprint in kind of this building resilience after natural disasters.
And if you're interested in more details, John Turpak with the Fish and Wildlife Service Gulf Restoration Program, as well as Greg Elliott with the Gulf Coastal Plains and Ozarks LCC have recently blogged about this news, including posting the interior press release. And John has provided a little more information on what this means for LCCs and why it's a big win for the South Atlantic and the blueprint. That'll be in this month's newsletter as well. So before I let everyone go, I just want to give you a sneak peek of next month's web forum. We'll be hearing from Brad Pickens, who's a postdoc with both the North Carolina State University Cooperative Fish and Wildlife Research Unit as well as the South Atlantic LCC, and he'll be presenting on advancing species distribution models to identify restoration sites for Bachman's sparrow in an urbanizing environment. So I'm sure everyone's familiar with the major reduction of the historic range of the fire-dependent longleaf pine savanna ecosystem, and great emphasis has been placed on restoration in recent years. While meanwhile, there's enormous urban development continuing in the southeast, which is really driving the need to improve our understanding of the types of conflicts that arise among current ecological condition, restoration potential, and urbanization. So Brad is doing this case study of one of the South Atlantic ecosystem indicators, the Bachman sparrow, and he'll discuss how he's applied the most cutting-edge techniques for modeling species distribution so that we can gain that critical knowledge for both on-the-ground management and broad-scale conservation planning. So he's been working to quantify species-habitat relationships, develop a species distribution model, project management scenarios, and look at the effect of urbanization from 2010 to 2090. And he's been working not only with the South Atlantic LCC, but with the North Carolina Wildlife Resources Commission, the Nature Conservancy, and NC State University. So next month, he'll be sharing the results from his scenarios and discuss the implications of his results for the South Atlantic LCC's Conservation Blueprint 2.0. So that's going to be a really great talk if you're interested in pine savanna, if you're interested in Bachman sparrow or ecological indicators, and some of the testing that's been going on to refine the blueprint. And I always like to end making sure folks know how you can get involved. Join our web community if you haven't already. Chances are if you're getting the reminder emails for this web forum and you're on the line today, you're already a member. But if not, I'd encourage you to join. It'll get you added to the mailing list for our newsletter and for the web forum reminder. You can always connect with a staff member, with me, with Rua, with Amy, Louise, Brad, Christy, any of the other staff folks that are on the line. And you can always communicate with one of your steering committee members to get your organization more involved. So thank you so much for joining us. Are there any questions about LCC stuff in general before we call it a day? Great. Well, it's 11 o'clock. Really appreciate you guys getting on the phone. I hope you enjoyed Ashton's talk today, and hopefully we'll see you in September. Bye, everybody.